you can see all the lectures recordings have been shared for last year. Okay, so if you are wondering, okay, or maybe you just want to know further before you enter this class, you can just take time to browse through it as well. Okay, all right. Okay, so we started with the recording. Okay, so today we will just quickly go through the last part of this chapter 2 on the block diagrams, right? So here, as you can see, yes, okay, so what we have gone through previously is we form or simplify our block diagrams through whether shifting it, okay, the blocks from one side to another side, okay, of the summing junctions, okay, or the take off points, all right, as well as we identify whether it is a this kind of a closed loop format, okay, or formation. So we can again further group them into a simpler equivalence block diagram, right? So you can see that this one we can simplify as a G over 1 plus, okay, since this is a minus kind of feedback, so 1 plus G 1 2, right? Okay. Then beside that, we also look into how we can total the block diagram that are in series as well as in parallel form. Okay. So today's just to complete this simplifications of the block diagrams. Okay, we will look into the closed loop system subjected to disturbance. Okay, so basically this disturbance can be inserted into any segment of the block diagrams, right? So as you can see, when there is a disturbance, okay, this is where you can see all the signals has been flowing, okay, from different directions. Okay, this is where you can insert the disturbance, okay, maybe from this point, okay, or the other points onwards. That's why we need this kind of simplifications, okay, to help us to deal with all the different directions of signal, okay, coming from maybe from inputs, okay, or maybe from disturbance, or maybe from multiple inputs, okay, to our system. All right, so here when we say two or more inputs are presented in a linear system, okay, so each input can be treated independently, right? So this is our ideas, okay, on how we can deal with disturbance. Okay, so when we have more than two inputs, okay, two or more inputs, okay, we just treat them individually, okay, or independently, so that we can total them up together, okay. Okay, we can add them up together to complete the whole outputs, okay, or to find the so-called superimposed kind of output, okay, from all these inputs. Okay, so the way each input is introduced in the systems at the summing point can be by either a plus or minus sign. Okay, so this is an examples of where we can insert a disturbance. All right, so we have a typical closed loop block diagram, right? Closed loop block diagram, but we would like to inject additional inputs over here. So we describe that as a disturbance. Okay, so this disturbance, okay, we have additions of signal into our system. Okay, just in between these two block diagram, right, or two transfer functions. Okay, so what we can do now, okay, we would like to identify, okay, what is the effect of this disturbance ds. Okay, we put them as a ds. Okay, so here what we would do, okay, to investigate this, the effect of only this disturbance, you can see that we in this system we have two input. One is the disturbance and the normal input, okay, from our typical block diagram, the rs. Okay, in order to only seeing this kind of effect, okay, so we will assume that this input rs is equals to 0. Okay, so this is how we can treat this system independently. Okay, so we assume that this doesn't exist. Okay, so this rs doesn't exist, then we will form this kind of loop, right? But then our main objective is to see how it will affect the output, the cs over here, right? So therefore, if this rs is not visible anymore, okay, let's take this into zero. Therefore, our input system, okay, as you can visualize later on, okay, you just assume that this is the disturbance, okay, the ds, okay. Then you have a block diagram, okay, which is this g2, right? So g2, and this is our target output that we would like to investigate, cs, okay. But then what happened is that there is a loop coming back, right? But then now the loop is involving h as well as g1, okay. So basically it's just going to two block. So two block, what we can do, multiply them together, right? So this is basically a g1 and h1, okay. So coming back to the system, so basically the similar form of closed loop system, okay. Therefore we have the output, the output, the c, okay. We denote that with a d because we would like to know that this output is due to the mainly the effect of the disturbance only, right? So we put cd equals to the g at the upper side, okay, divide by 1 plus, okay, since this is a negative kind of input over here, okay, minus over here, right? So eventually we have minus over here, right? So when we total them up, we have 1 plus the upper multiplied by the lower, which is the g1h. So we have g1, g2, and h, right? To form this kind of transfer functions as the effect due to only the disturbance. Okay, so here you can see that in the case that the GH is very large, okay, or large, very large, larger than the one, or and also this G1, G2, and H1 is very large, okay, as compared to one, okay, the closed loop transfer function will become sort of like zero, okay, when this is very large, okay, then eventually it becomes zero, okay, this whole functions, okay. This means the effect of disturbance is surprise, okay. This is an an event an advantages, okay, of a closed loop system, right? So what it means is that if we would like to minimize the effect of this disturbance, okay, when this disturbance is being inserted, okay, how we could minimize the effect of the disturbance is we increase this transfer functions, okay. If they are very large, okay, large enough, okay, therefore the effect due to the disturbance is almost zero, okay. So we would say that the transfer function is now large enough to suppress we say that the keyword is to suppress the disturbance, okay. The disturbance is too small, okay, to have any effect on that, okay. This is the benefit of having a closed loop system. Okay, so after that, okay, we also consider when the disturbance is not there. Okay, so when the disturbance is not there, then we just treat the disturbance is should be, sorry, this should be d. Okay, this should be d, right? Because we now assume the disturbance is zero. Okay, therefore, as normal, all right, the upper side, the forward side, okay, so g1 g2 divide by 1 plus the lower side multiplied by the upper side, right? So G1, G2, and H. Okay, so therefore from these combinations, what we can do next would be in the case, or yeah, how we can analyze this is that in in the case of this particular component, okay, the G1, G2 divided by H, okay, G1, G2 divided by H, this particular component, okay, increase, okay, it will cause the transfer functions to be approaching 1 over h, okay. So what we can do from this, okay, is again we would like to increase these two transfer function, okay, such that is so much higher than 1. Okay, so G1 and multiply by H much larger than 1, right? Then the closed loop transfer functions now, as you can see, if we increase this G1 and H much larger than 1, the disturbance can be somehow ignored. Okay, and at the same time, the closed loop transfer function will be mainly independent to the uh, or inversely proportional to the 1 over h. Okay, so this is the idea of why if we could increase this one, okay, much higher, okay, than once, because maybe had a hash we cannot increase much. Therefore, from these two multiplications, it would be much greater than 1. Okay, and this would be the normally this transfer function is our controller. Okay, this is where we would like to control our system such that our closed loop system is stable, as well as it can minimize the effect of disturbance to our system. Right, so this is the benefit of having a closed loop system. Okay, so as a total, or as a uh, yeah, simultaneous effect of both applications of input as well as the disturbance, we can sum them up together. Okay, the CR as well as the CD, just total them up together, you would roughly get this kind of transfer functions. Okay, the next part would be the signal flow graph. Okay, as I mentioned previously, I would not go through this, okay, in detail, okay, because we would not use this signal flow to analyze our system. Okay, but the idea would be this signal flow concept is similar to the block diagram. Okay, the only difference is that instead of using block, they use branches and nodes. Okay, the nodes now is the representing the signal. Okay, in the block diagram, we use arrow to represent the signal. Okay, and we use the so-called block to represent the system, right? Okay, here the signal flow is slightly different. Okay, they would use the node to represent the signal, okay, and the branch, okay, to represent the transfer function. So you would write the transfer function over here. Previously is here, okay. You would write it over here, okay, just at the branch itself. Okay, so it will connect from one node to another. Okay, so that is how it would be being translated. Okay, instead of signal going in, okay, to a block, okay, they just use node as well as the branch, okay, to signify the transfer functions. Okay, so this is how it would looks like, right? So I will not go through into details on all these things. Okay, so you can test on this on your own, right? How you would like to uh, form this kind of block diagram into the signal flow, right? So you have the signal RS, okay, as a node, okay, go through the block, so it will be represented by the branch or the line, right? So you just write the transfer functions on the line. Okay, so this is how it would looks like. Okay, okay, so you can always go through those examples. Okay, so any questions for the block diagrams part and the disturbance while I'm switching to another slide? If no, then we just proceed with the second uh, slides. Okay, so this would be our chapter 3, okay, which is related to the time response. Okay, so time response would be the first sign or first type of analysis. Okay, after we form the block diagrams, okay, what next would be we would like to know what happens, okay, to our system when a, ca- a, s- a type of input, okay, or signal being inserted to our system. Okay, this is we would like to know the response of it. Okay, we call that as a time response. Okay, so the goal of this chapter would be to analyze the transient response. Okay, the transient response part of the system. system, okay, before we would proceed to another chapter to cater for the steady state error itself. Okay, so our main part would be to analyze the transient response. Okay, but just a little bit of planning for these courses, right? So currently we are at week number 3. Okay, we are at week number 3. Okay, so in this course planning, okay, for this semester, in order for you to avoid, okay, sub having all the tasks at the same time, okay, basically we have discussed and arranged, okay, such that uh for third year courses, okay, we would like to have like maybe one, maybe at most 2 tests at one single week lah, okay. So for this course, okay, we would have estimated the test one would be on week 5, okay, 2 weeks from now. Okay, then the second test would be at week 9. Okay, then on the assignment, as I mentioned previously, okay, you would have like a continuous type of assignment. Okay, you just top up, okay, when I give you a task and so on, right? So basically the assignment you just have to submit at the end of this semester, okay, and week 13. Okay, but to make sure your progress is correct, okay, I would like you to submit what you have done on week 4. Okay, on week 4 first, okay, the part 1 of it, okay, so that I can give you feedback, okay, so that you can tune it or rectify it accordingly before you proceed with the the second part of the analysis as well as the design of the controller. Okay, so in order for you to submit as a final assignment at that time, right? So be clear that this assignment part 1 you have to submit it, okay, on week 4, end of week 4, okay, which is next week. Yeah, end of next week. Okay, yeah, end of next week. The time I would set it later on, right? So you just submit what you have done so far, okay, so that I can go through it and give you feedback on that. Okay, so okay, as a part of the assignment, okay, on the first week I've show you some of the videos on the robot grippers, right? Okay, and I told you to get some ideas, okay, to describe the system of the robot grippers. Okay, so what you need to do now, okay, to submit as the part 1 would be from that robot grippers idea, okay, now show them in the form of block diagram. Okay, form in the form of block diagram. Now you can start to visualize that what type of input you would like to get, okay, whether there is a sensors or not. Okay, so make a simple closed loop system so that you can do a controls later on, right? So basically as a hint for you, okay, I may expect or something something very similar to, sorry, okay, to the previous one, okay, the one with disturbance, right? Okay, so this is your output, okay, you have your feedback, right? So it can be as simple as this. Okay, what you need to do is only show your block diagram and form all these transfer functions. Okay, how to get all these transfer functions? Either you search it from maybe papers or maybe from any related uh, materials. Okay, you just say citations. Okay, maybe this is related to the motor transfer functions. Okay, so you just cite this transfer function is from reference A. Okay, reference A transfer function is like this. Okay, so this controller is unknown, right? So you just put anything you like. Okay, this feedback, okay, it can be due to a sensor, so you can get it from any reference, okay, related to you. Okay, so this is what you need to do. Okay, just show the block diagram, describe your system previously as I've told you to do so. Okay, then now you show the block diagram. Okay, and after this I will show you on how to analyze the time response. Okay, so what you need to do is, after you have this block diagram, you just put them into a simulation software. Okay, and just run it. Okay, get some graph from there, and from the graph, okay, in this chapter we will learn how to like getting the those time response characteristics, okay, of your system. Okay, just show that simple part, right? So any question for this? If no, okay, then we will move on. Okay, right. So as a part of this chapter, okay, we will rely more on the software, okay, which you would use it, okay, in the assignment as well as in the lab 5 next year. Okay, lab 5 for the control would be more on using simulations, okay, to simulate the system, okay, in order for you to control it later on, right? So here, as I've mentioned earlier, okay, we can use either MATLAB plus Simulink, okay, or you can also use open source software, a freeware, okay, Scilab plus Xcos. Okay, so MATLAB mainly is a software to solve matrix kind of mathematics problem. Okay, so similarly, Scilab is designed very similar to the MATLAB. Okay, so what is the Simulink is an extension of the MATLAB. Okay, where they can now uh, use the kind of a drag and drop, okay, of the blocks. Okay, this is where the block diagram become useful. Okay, you just drag and drop, okay, double click, then you can type in the transfer functions from there. Okay, in order for you to simulate, okay, so they call it Simulink, okay, in the MATLAB. Okay, as the some kind of similarity in the Simulink, okay, together with the Scilab is the Xcos. Okay, again similar. Okay, they can accept the block diagram. Okay, double click, change the parameters, and so on. Right. So what you need to do after this is just follow. Okay, either you are using Windows or maybe you are using Mac. Okay, so just install accordingly. Okay, but I think for these instructions a little bit outdated, but nevertheless they can be applicable, right? I guess now the Scilab version would be 6.13, 6.13 if I recall correctly, or 6.3. I yeah. So just download, okay, from the website. Okay, just install accordingly, right? So for the Mac, for the if you are using Mac, then you may need to install additional uh, add-ons lah, okay, on the Adobe OpenJDK Java Development Kit, as well as the Scilab, and also a little bit modifications on this, okay, so that they to allows you to read the folders, okay, on your Mac, okay, yeah, on your Mac according to yeah, sorry, accessing the folders on your Mac, okay, inside the Scilab itself. Okay, so probably I just show you the interface, okay, so that you can see it directly, right? So this is the Scilab interface. Okay, what I mean is that the folders, okay, here you can see the folders in my computer, okay, inside the Scilab, right? So this is where, that's why you may need to do this for Mac, okay? But for Windows, you don't have this problem, okay? So you can access it anywhere, like Okay, so you can see the folders inside from one point to another. Okay, so now next would be a quick tutorials on this, okay, on how to use this software itself. Okay, in this software, one point that we would like to use, okay, or why we would like to use this software would be to solve simultaneous equations. Okay, this is the very important uh, math functions, okay, that's required for any engineering problem, okay, especially when you are dealing with finite elements later on. Okay, you would need to solve a lot of simultaneous equations, okay, in order for you to get the solutions. All right, so let's take this as an example. All right, so in mathematics you would know that if you would like to have a maybe a matrix, okay, or a symbol a multiplied by x equals to y. Okay, so if you would like to know what is y, then you can rearrange such that y is equals to the this one moving on the other side is the inverse a, right, multiplied by y. Okay, so this is how you can rearrange it. Okay, but remember, in programming, we the computer will never understand this. Okay, x multiplied by a multiplied by x on the left hand side. Okay, they will only accept a terms equals to whatever equations you have on the right hand side. Okay, therefore in these equations, if I type these equations over here, okay, a multiplied by x equals to y, they will not understand, okay, because they expect an equal, right, over here. Okay, so they may expect something like this: a equals to y multiplied by x. They may expect in this way, but what is the problem is that they do not know what is x and y probably. Okay, because you never tell in this software what is x and y. Okay, this is why you have to define them earlier, right? So what you can do now, okay, as a start, okay, you may start to define all your a. All right, so probably I would like to define them in a matrix form, right? So let's say my a is a 3 by 3 matrix. Okay, so I have 1 2 3 4 5 6 6 5 4, let's say. Okay, then the x is the kind of unknown, so you may multiply by unknown x1, okay, x2 and x3. Okay, so this is equals to, let's say this is 4 3 2. Okay, let's say this is our equation. So is this matrix I would say compatible? I would say yes. Okay, this is 3 by 3 multiplied by 3 by 1. Okay, it should give us a 3 by 1 equation as well, right? Okay, so how we can program it over here, okay, so or define that it over there is that we you can see that this is a, right? So we will say that a equals to, we put a bracket. Okay, so we put 1 space 2 space 3, okay, semicolon, then 4 space 5 space 6, okay, semicolon, then 6 space 5 space 4, close, right? So in the examples over here that I show over here, I put a semicolon over here, right? So yeah, okay, let's try not to put a semicolon. What it would do is it will show the matrix. Okay, so is this matrix same? 1 2 3 4 5 6 6 5 4. Okay, if it is same, then it's good. Okay, if it is not same, what you can do, you just press your arrow button in your keyboard. Okay, you can put up up up, so you can select the all the equations that you have typed previously. Okay, right, so if it is not correct, so you just change it Okay, let's say this is, I would like to change to 5. Okay, and if you put semicolon, what happens is that they will save your line. Okay, so it will store in their memory, in the computer memory, but it will not display now. Okay, previously without the semicolon it will display. Okay, but if you put a semicolon over here, it will store but not display, right? So if you want to know whether your A is correct, you just type A. Okay, then it will tell you what is A. Okay, so you can see that I changed to 5. Now this 4 changed to 5, right? This is what that have been stored in the memory. Okay. Next would be, we would like to define the y that we have here, right? So we can define y equals to, again, semicolon, sorry, bracket 4, semicolon 3, semicolon 2, right? This is what we want. And now we are very confident. We just put semicolon so that it doesn't display, right? So in order to get the x, okay, we just follow this because we would like to rearrange, right? So we have x equals to inverse. This inverse is already a built-in function in Scilab or MATLAB. Okay, so you just use it, then it will compute the inverse matrix for you and multiply by y. Okay, so if you put a semicolon, then it will solve the x but not displaying the x. Okay, but if you would like to know what is the answer of x, just put without semicolon, so you get your answer. Okay, x1 equals to 3.6666, x2 equals minus 12. Okay, x3 is 8.13, 8.3, and so on. Okay, so this is very useful when you are dealing with maybe tens or 20 kind of equations together. Okay, just put them in matrix, and this will help you to solve it simultaneously, right? Okay, so other operations of matrix would be like, you can generate rows. Okay, you can put like a equals to 1 dot dot 5. Okay, 1 dot dot 5 means it will generate a from 1, 2, 3, 4, 5. Okay, so this is how it would looks like. Okay, you can also generate in a step form, meaning to say, if this one by automatically it will increase by one by one by one by one, right? But if you would like to increase by a certain step, okay, let's say you would like to increase by 0.1 every time, okay, or maybe 0.2 every time, so you just put dot dot 0.1 or 0.2 dot dot. Okay, so it will generate accordingly. Okay, then if you have 1 and 2 together and you would like to combine them together, you just put it in this way. Okay, if you put this dot dot, then it represent 2 rows, right? Okay, but if you without this, then it will continues from there. Okay, and then if you would like to extract the exact numbers or members, okay, as like in the programming, then let's say you would know what would you like to know what is stored in the in a element number 3. Okay, so if you check, okay, a answer or a matrix itself, element number 3, 1, 2, 3, so you would get the number 3, right? So this is how you get number 3. Okay, or if you like to get a from element number 3 to 5, okay, 3 to 5 is, okay, coincidentally 3 to 5. Okay, so you can try all these things, okay, on your own to check out, okay, what you can do in the software, okay, using matrix operations. Okay. Next would be polynomial, right? So what I have shown you previously is when there is a number, okay, you solve using a number, okay, but then when certain times, okay, just like us, okay, we deal with x, y, okay, where it is a polynomial without any numbers. Okay, so what we can do is we would define that like this. Okay, we would tell that x is a kind of polynomial. Okay, so you type poly bracket 0 with a symbol of x. Okay, then meaning to say they will know that x that you put is an x, is not a number. Okay, x is an x. Okay, it's not a number, right? Or otherwise they will always ask you for a number. They will say error, it's not a number. All right, Then second thing would be after you type this one, now they know x is not a number, okay, but an x. Therefore, they can accept this. Okay, you can type d equals to x power 2, okay, plus x times 2 plus 2. Okay, eventually they will form in this way. Okay, so this represent that this is to the power of 2. This is sorry, this is power of 2 power 1, and this is the initial one, right? They will store in the matrix in this form. Okay, otherwise they will keep telling you something is wrong with the equations. Okay, so we can again try, if we do not define the polynomial, what would happen, right? Okay, so we just continue just to type d equals to x to the power of 2 plus 2 times x plus 2. Okay. Oh, coincidentally, we already have x. Ah, okay. Sorry, we already have x over there. Then they will calculate. Okay. If let's say now, what I can do is I will clear. Right. So clear my memory. Okay. Just clear. All right. So now my memory doesn't have x. Just try. Okay. X is unknown. Okay. So let's try again. Now you can see that they expect a numbers of x, okay, but you do not see any x over there. Okay, so the software will tell you undefined variable x. Okay, unless initially say that x equals to poly 0 and it is x. Okay, so now if you apply the same equations, now it will accept. Okay, so accordingly to this, therefore you can also find the coefficients of d. Okay, so you only need the numbers, then we call it as a coefficient of d. Okay, without showing the x and the x prime, or maybe if you would like to solve it now, okay, remember you can also solve them. Okay, just assuming this is equals to 0. Okay, a normal second order polynomial, right? Or quadratic equations, you just type roots, bracket the d, then they will solve it for you. Okay, is it very convenient, right? Okay, so this is where you can use your software, right? So now let's say you want to solve roots, okay, the d. Okay, so the answer would be with imaginary values, right? Okay, so immediately you know that sometimes there is with imaginary values, sometimes it doesn't. Okay, so in our case here, there is an imaginary values, but in these examples, they do not have any imaginary values, 0, right? So eventually, all the values is the real values, okay, for the x, the roots 1 and the roots number 2. Okay, so same thing you can also do in this way in the fractions as well. Okay. Now next would be how you can see the x cost. All right. So since I'm using Mac, okay, but for sure in Windows it's the same. Okay, I've tried that as well in Windows. Okay, so you just go to the manual, look for the applications, and look for x cost. Okay, once you press it, then you should see something like this. Okay, and here you can see the similar form of diagram, okay, or blocks. Okay, so what you can do is later on you just drag. Okay, so this is a summing point. Okay, two values, okay, total them up together. Okay, summing point, you can show the graph, okay, where how it would respond. Okay, you can insert a kind of a signal, a constant value of 1. Okay, if you insert a constant value of 1, means you are putting a step input, right? Okay, so this is how you can insert all these things. Okay, you just click. Okay, look for the typical kind of blocks diagram. Okay, just drag and drop, drag. All right, so you will able to run it. Okay, so yeah, again, this is how, let's say I'm using this, okay, a step input or a step functions over here. Okay, so what you can do is just a practice later on. After you install, you just quickly run or play around before you you work on the assignment, right? Okay, you look for clock underscore C, okay, and step underscore function from the source palette. Okay, source palette means you just go palette, source palette. Okay, you can see source palette. Uh, okay, just click it, then you should able to find the clock and the step, right? Just drag it out. Okay, drag it out. Okay, so this is clock, this is the step. Okay, then also you look for the C scope. Okay, so C scope, this is how it looks like in the sync palette. Okay, big sum functions. Okay, from the mathematics, just now you saw it. Okay, you just drag it out. Okay, and this one, let's check. I think that one is just the normal transfer functions. Uh, Yeah, okay, normal transfer functions. Just you just drag a block over there, okay, then you can start to type it on your own. Okay, so once you have done that, you just try to how modify them together. Okay, for example, for the big sum itself, the big sum block itself. Okay, big sum block is this one, right? Okay, you can modify from plus plus to plus minus. Okay, what you need to do is just modify this. Okay, whether plus one or minus one. Okay, if you want to have plus plus, then you just remove the one over there. Remove the minus over there, sorry. Okay, then the rest would be the line. Okay, the line is you just use your mouse pointer, you click, okay, then you drag until the other point. Okay, you release, then they form the arrow for you. Okay, very convenient. Okay, then for this transfer functions, okay, you just look for the seesaw, continuous seesaw transfer parameters. Okay, therefore you can insert what is your numerators. Okay, you can put 1 plus s. Okay, 1 plus s power of 2. Okay, remember, uh in control we use a lot of s, okay, as the Laplace transform form of parameters, right? Same thing in xcos as well as in Simulink. Okay, they understand s but not other parameters. Okay, they may understand t as well. Okay, but if you put a k, they will not understand, right? So you have to do something like this lah, some sort of this way. Okay, so after you run this, okay, everything complete, then you just look for a button, simulate or run. Okay, then probably they will show you this. Okay, by double clicking this oscilloscope, okay, or comscope, okay, C scope, then you would see the signal. It's actually like this. Okay, you would see how it would behave after how many seconds, and from here, okay, you will know that after probably 4 seconds, okay, probably 4 seconds, it's already reached the steady state. Okay, and so on. Okay, and this is what we would use and learn to analyze, okay, throughout this time response. Okay, and this is what I call as a time response, because it throughout the time how it would respond. Okay, so this is what we would do, okay, in these chapters. Okay, other functions, you can try PLZR, okay, the polar form of a plot and other things. Okay, these are the related type of functions available in Scilab, okay, for us to do our analysis of control. Okay, control. Okay, so there are a lot. Okay, but just get familiar with the previous few functions first. Okay, then slowly after you can understand, you can start to explore further. Okay, how to explore further is just in the console. Just now you just type help. Okay, you just scream help over there and with your functions. Okay, so for example, okay, now you're not sure how to use the roots. Okay, you just help roots. Okay, then it will display a help browser for you, telling you how to use the roots, okay, how it would accept the parameters and so on. Okay, they will list out the all the things for you. Okay, just type help and the functions. Okay, then it will tells you, right? So any questions about the software now?
No, sir.
No, doctor.
Okay, that's great. Okay, so once that is clear, then probably we would start with our lectures. Okay, so our lectures today would be on the time response, right? Okay, so sorry. Okay. Okay. So time response. So our time response, what is our purpose is to find the output, okay, how it would behave, okay, when we have response coming into our system. Okay. We would divide the input type of response or the output type of response into two. Okay. The first one would be the forced response and the second one is the natural response. Okay, the first response we would also call it as a steady state response. Okay, or response or responsible for the steady state response. Okay, whereas the natural response is the homogeneous response. Okay, so you may not see this clearly now over here, but slowly we would form those kind of equations to separate them. Okay, and you will see how they can sum up as as an output, okay, together. Okay, the fundamentals to the analysis and the design of the control systems relies on several concepts. Okay, one of it is pull and zeros. Okay, the pull and the zeros. Okay, that simplify the evaluations of a simple system response. Okay, the pulls and zeros are based on the transfer functions. Okay, what it looks like is that, okay, in our transfer function. Okay, maybe before we move into this concept, the idea why we use the pull and zero is that in Xcos and MATLAB and so on, right? You would simulate so that it will show this curve for you. Okay, but this concept of pull and zero actually exists long time back. Okay, to help designer. Okay, to give them an idea such that even without plotting out, okay, without plotting out, we can already see the kind of response, okay, or we can expect what kind of response would occurs from there. Okay, this is the concept of the pulse and zero and why we would use it, okay, before we just simulate. Okay, but nowadays since we everyone can have a direct access to software and computers, yeah, then maybe this would be, I would say, die off technique soon or later, right? But then, uh, yeah, it form a kind of concept such that it give you the intuitions, okay? One meaning to say, once you see an equation, okay, you can immediately break them into poles and zeros, and you would roughly estimate what kind of response you would expect, okay, without plotting out. Okay, this is the idea of this poles and zeros. Okay, so the poles would be uh, referring to the Laplace transform variables, okay, that cause the transfer functions to be infinite. Okay, if you would like these transfer functions to be infinite, what you would do? You would turn the denominators into zeros, right? Okay, meaning to say, if you put zero, this whole transfer function will become infinite. Okay, if you put negative 3, okay, negative 3 plus 3, okay, is 0, right? So again, negative 3 will turn this whole transfer function into 0, into infinite. Okay, so all this would, we would call this as a pools. Okay, so for a transfer function itself, okay, where or usually we will form in this way so that we can easily identify the pools. Okay, then from there, we would know the roots of the denominators of the transfer functions, okay, and we would plot them out on this what we call as S-plane, S-plane, okay, S-plane itself, or S graph lah, all right, S type of graph itself, okay. So in this S graph, okay, once you start to plot it, okay, plot the axis, okay, instead of using X and Y, use the sigma and J omega. Okay, so this sigma represent the real values and this represent the imaginary values. Okay, so this is the S plane, okay, to denote all these S parameters or variables itself. Okay, so since the pools is 0, but 0, 2, and minus 3, right? So you just put cross to represent the pool. Okay, on this S plane, we put a cross to represent the pools. Okay, so you put minus 3, 0, and 2. Okay, then next would be the 0. The 0 is the one that turn the whole transfer function into 0. Okay, meaning to say the upper or the numerator part. Okay, if you have the s equals to 2, then 2 minus 2 becomes 0. Okay, no matter what you have at the bottom, the whole transfer function still becomes 0, right? So therefore the s or the 0 will be 2 over here. So for the 0, we will represent it with a circle. Okay, a cross and a circle, right? Very simple, right? Just like the cross circle game, right? Okay, so just put it on the S plane itself, all right? So that is our poles and zeros, okay? Now, as I mentioned to you, we try to look at the poles and zeros, okay, such that it will give you the ideas, okay, on how it would looks like, okay? So let's take this simple transfer function as an examples. Okay, so we have s plus 2 and s plus 5. So our 0 would be minus 2 and our pool would be minus 5. Okay, if we draw it properly in our s plane, then we would have minus 2 with a circle and minus 5 with a cross over here. Okay, so very straightforward, right? Okay, so what happened is that if you would like to see the properties of the pool and the zero, uh, we use the kind of unit step response, okay, into our system. Okay, just put a step response to our system. I simulate this using the X course itself. Okay, draw a very simple input, no need feedback because we only want to test this transfer function, right? Signal to the transfer function and see what is the response itself. Okay, so immediately you will see this kind of response. Okay, so what in real or mathematically exists is that this transfer functions, okay, when we couple it with a step input is 1 over s, okay, 1 over s, therefore our output will be s plus 2 divided by s multiplied by s plus 5. Okay, therefore this would be our whole output, okay, from this particular block diagram. Okay, from this fraction itself we can put them into a partial fractions consists of a over s and b over s plus 5. Okay, so this is where you need to use your knowledge on the partial fractions. Okay, break them into parts. Okay, so you have 2 over 5 and 3 over 5. Okay, so if we do uh the reconversions from the Laplace transform into the time domain, okay, from s domain into the time domain, therefore you will have the 2 over 5, okay, to represent this part, as well as the 3 over 5 multiplied by the exponential of minus 5, okay, minus 5t. Okay, so in this equation itself, what you would see is that this front part is the forced response. Okay, meaning to say no matter what is the time, okay, you would have this effect, okay, applied or a constant applied to your output or to your time response itself. Okay, whereas this natural response would be the oscillating part. Okay, that depends on the time, right? So I again use the Scilab. Okay, if you want to simulate this graph, okay, you just follow this, okay, or copy and paste this, okay, into your Scilab, okay, type line by line, okay. I recommend you to type, okay, instead of copy paste, okay. Type so that sometimes you may encounter some errors and you try to debug on that, right? So eventually you can plot this graph, right? And this is how it looks like, okay. On the whole response itself, on the whole response that we generate, okay, is a line from 1 drop to maybe 0.5, okay. Yeah, 2 over, so sorry, 0.4, okay, because this is the force response that responsible for the steady state itself, okay, that we have mentioned previously, okay. So if you eventually come to a point where it become a steady value of 0.4, okay, and that particular steady value itself is being represented by this blue dot, okay. So eventually this is the one that govern the steady state, okay, or the force response itself, okay. Whereas the natural response, okay, it will die off, okay, if we reach the steady state, okay. So it will come from 0.6, then slowly drop until the becomes zero, okay. So eventually when we total up this force response as well as the natural response together, you will see this red line, okay, which is corresponding to this particular line, okay. Meaning to say, what we have calculated in maths, okay, mathematically, okay, we form these equations, we plot them out, is exactly the same with the what is being simulated by the x cos, okay. This x cos, I do not put any equations, right? I only put the transfer functions, the step, and it generate this line for me, okay. But this technique is I would use in Scilab, okay, the console itself, the one that I showed you previously. Sorry, the one with where I can type, okay, I type it, okay, according to all these parameter, okay, 2 over 5, okay, the 3 over 5 to exponential and so on. I type them accordingly, and when I total them up, I get this line exactly the same, right? Meaning to say, what we have theoretically compute and what have been simulated by the equation stored inside the software is the same, okay. This is important because software itself is still being programmed by human, okay. Sometimes the software may have bugs, okay, even though it's very expensive licensed software, okay, it's still being programmed by human, okay. That's why we somehow need to have the fundamentals, okay, to support or to verify whether it's correct or not, okay. So this shows that they are correct now, right? Now if you would like to plot the S plane, okay, S plane now, okay, the previous X plane, this S plane using Scilab, again you can use this, okay, type in the Scilab, okay, type accordingly, then you use the function plzr, okay, then it will plot this for you, okay. Then you can see that it shows that the the so-called zeros would be at -2, the pole would be at -5, okay. This is generated by the Scilab, okay. So how we can draw conclusions, okay, is that the pole, okay, the pole, now the pole is this one, okay, the pole of the input forms the force response, okay, the one that responsible for the steady state, okay. So we can say that a pool of the transfer functions, okay, a pool of the input, okay, this input 1 over s form the force response, okay, a pool of the transfer function, this is our transfer functions, will generate the natural response, okay, the pool, the bottom one, s plus 5, we generate the natural response. The pool from the input, the s itself, will form the force response, okay. So a pole on the real axis now, okay, this real axis, a pole on the real axis generate an exponential type, okay, so you will see the e minus the numbers over there, okay, where these numbers depending on the locations lah, of your real axis, okay, meaning to say now by looking at the pole itself, you immediately know that it is an exponential type of response, okay, exponential type meaning this type lah, okay, going down, okay, because this is minus, okay, so minus is go down, okay, if this is plus then goes up, right? So immediately you can see this form, okay, imagine directly in your mind such that you see a pole, you see this format, okay, e exponential minus the alpha t, okay, if this is 2, sorry, this is yeah, 2, then it's 2 lah, okay, but then this is x is 5, then this would be 5 over there, okay. And what happens is that the further the further the to the left hand side of the pool, left hand side is over here, okay, because we always look at the negative side, okay. Most of the time we would like our pools and zero on the negative segment, okay. Later on, slowly you will know why we prefer it on the negative segment, okay. The further it is on the left to the pools on the negative real axis, the faster the response, okay, the faster the response to become zero, okay, response to become zero very fast, okay, meaning to say it reach the steady state faster. Okay. And then also the zero and pulse will generate the amplitude for both the force and natural response. Okay. So from this particular combinations, okay, if there is input pole, okay, at the zero itself, okay, it contribute to the force response. Okay. When there is a pulse on the transfer functions, it contribute to the exponential decay of the natural response. Okay, where the zeros now is determining the how how much or yeah how much it will react, okay, according to that to force as well as the natural response. Okay, so again take this examples again, given a system in this figure, write the output in a general terms, okay, in the general terms meaning to say in this time response format. Okay, so what you need to do is transfer functions, a very straightforward open loop forward uh, system, okay, you have a step input, okay, 1 over s, you just have to multiply them together, okay, and then break them into the partial fractions, okay, so when you break them into partial fractions you would see this form, this format, okay, and immediately you would see that the force response is due to this 1 over s, okay, and it would corresponding to the constant, okay, whereas the rest would corresponding to the exponential terms, okay, if this is plus 2 then it become minus 2, plus 4 it become minus 4 and so on, okay, so if you have 10 of this then you have 10 of this, okay, of exponential response being accumulated together or plus together, okay, so you can always again simulate it, okay, so you would see that this is how it would looks like, okay, this is how it would looks like from 0 to uh yeah 0 to something 0.7, okay, or 0, yeah, 0.7 something, okay. So would be how it looks like, okay. So any questions so far on that pulse and zero?
No, Doctor.
Okay, that's great. Okay, so next we would just go through the first part of this chapter, which is on the first order system. Okay, so on the first order system, okay, previously you can see that we have multiples of all these things, right? Okay, for a first order system, we would only consider one of these. Okay, one plus A. All right, we would consider only one of this, so that we would say this is a first order system. Okay, if it's second order, then you have a square and so on coming into the transfer functions, right? So the first order system without a zero is given as such. Okay, and if the unit step is 1 over s, therefore the Laplace transform of the step response would be, you just multiply by the 1 over s, okay, you get this, right? So if you take inverse, then immediately this is equals to 1, and this is minus e, this is a over here, right? So minus at. Okay, immediately you see this kind of a typical step response, time response, okay, or step response. Okay, very similar. Okay, so this is how it would looks like. Okay, a over s plus a, okay, and so on. Next is the characteristic itself. Okay, when we would like to analyze for a first order system, okay, what we would like to investigate is three transient response performance or specification or characteristic. Okay, the first one would be the time constant, the second one would be the rise time, as well as the third one would be the settling time. Okay, so these three terms would occurs from time to time, especially towards the design. Okay, where uh, it will become a design criteria. Okay, for example, you want to tune your controller such that the settling time is within zero point 0.5 second. Okay, you want it to settle with as fast as possible. Okay, so that would become a characteristics of performance that you would desire for your whole system later on, right? So from the response equations over here, the step response or the time response, okay, for us, for uh first order system, okay, you can see that the t, when it is equals to 1 over a, okay, when the t is 1 over a, then this one will become minus 1, right? So when it become minus 1, is actually equals to 0.37. Okay, or in other words, okay, this is the whole picture of the response. 1 minus 0.37, it corresponding to a value of 0.63. Okay, so what is this 0.63 is that over here, okay, 0.63 is 63%. Okay, so what happened is, if you would like to find the time constant, okay, if you would like to find this a value, right? Now we put a general constant over there is a, right? Okay, if you would like to find the a values, okay, it defined by the time constant. Okay, the time constant is called as 1 over a. Okay, and the time constant can be described as the time for e minus a t to decay 37%. Okay, just like our previous equation, or correspondingly, it has rise to 63% of the final value. Okay, because our final value is 1. Okay, so it's already increased 63%. Okay, what it means is that this is our performance of the, let's say, first order equations. Okay, So later on, you just check this. I just randomly put a 2 over s plus 2 as my transfer functions. Okay. And this is the graph that I have generated. Okay. So in order for me to find the time constant, okay, I would take the 63%, okay, or in this case, one is my 100%, right? One is my 100%, sorry, one is my 100%, therefore 63% is 0.63. So if I take a dot 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 over here, then I take this value, okay, so this value is corresponding to 0.5, right? Okay, so 0.5 meaning to say my a my a value is, sorry, my uh time constant is 0.5. So 0.5 is equals to 1 over a, right? Therefore my a is equals to 1 divided by 0.5, I get 2, right? So this proof that my original equations or my original transfer functions would be 2 divided by s plus 2, okay? Because you get 2, right? Okay, and this is the definitions of the transfer functions. Okay, so this characteristic is important, okay, especially when you are doing an experiment. Okay, why I would say it's important to characterize a system, okay, to get this time constant is that many times we may not able to form all these equations, okay, we're not able to form all these equations mathematically through theory. Okay, so what we did or what we usually do, okay, is to do a testing of the performance. Okay, and from the testing itself, okay, we would generate this kind of graph. Okay, and from the graph itself we would able to identify what is the time constant. Okay, and from the time constant now, okay, we would know what is the transfer functions. Okay, and this is how we can get our transfer functions. Okay, that is the purpose of using the time constant, right? So here the a parameter, we call that as an exponential frequency. Okay, and yeah, the rest probably you can read it. Okay, so time constant can also evaluate from the pool plot now. Okay, so since the pool of the transfer function is at the minus a, okay, is at the minus a, okay, we can say that the pool is located at the reciprocal, means 1 over a time constant, and the further the pull from the imaginary axis, okay, again imaginary axis is this j omega, okay, this line, okay, the further it is away from the pole, okay, the faster it will have a transient response. Okay, that is the idea, right? So immediately from this, the further it is, okay, the faster the response. Okay, meaning to say, uh you would see for this one probably it's like this. Okay, for this one you would see it like this, faster. Okay, if it is further, then you would see further faster, right? That is the ideas of it. Okay, the second specifications that you would like to know would be the rise time. Okay, rise time is defined by the time for the wave, okay, from 0.1%, okay, or 10%, sorry, okay, to 90%. Okay, so we only look at this time period of time. Okay, this period of, sorry, go here 90%. Okay, so you only look at this length. Okay, so this would be our time, rise time. Okay, so normally either graphically we can get this, okay, or if you do not like these ideas, other way to get it would be generally for a first order system, we can simplify using this formula. Okay, 2.2 divided by a. Okay, if we know the a, then we can estimate the rise time. Okay, so for our previous case, our a is 2, therefore our rise time, if we put over 2 over here, then we roughly get 1.1, right? So this time is roughly 1.1 second. Okay, that is how we can estimate the rise time. Okay, the last specifications that we would cover today would be the settling time. Okay, for a settling time is referring to the time it's required to reach and stay within a 2% of its final value. Okay, remember, reach and stay within. Okay, because this is a first order system, so you would see that it doesn't oscillate that much. Okay, therefore it's very straightforward. 0.2 percent, this is 100. Okay, 0.2 plus minus, so this is a 0.98. Okay, or 1.02, right? Okay, plus minus, so 0.98 would be good enough over here. Okay, so meaning to say the settling time over here, okay, is roughly at this point. Okay, 0 point, 0.2. Okay, such that it will reach, or it can be further or better estimate as 4 over a. Okay, again, if you know the time constant. Okay, therefore knowing the time constant is very useful. Okay, for a system to identify the characteristic like the rise time as well as the settling time. Okay, other than the time constant, we can also graphically, as I mentioned. Okay, you just draw dot 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 dot. Okay, just make sure that when it start to reach and stay within that particular range, then you can start to measure. Okay, this would be the settling time from the starting point. Okay, how long it takes for it to reach. Okay, for first order, quite straightforward. Okay, but when we start to deal with a second order line, okay, then it will start to oscillate. Right, sorry, it will start to oscillate. Okay, therefore this 2% would be defined as such. Okay, the final steady state value, okay, plus minus 2%. Okay, so you will see that at certain point, okay, this graph will start to fall within that. Okay, so you just maybe probably this point. Okay, so this would be the settling time. Okay, to define for a system where it would always oscillate. Okay, and settle down. Okay, but for a system where it will continue to grow, okay, then they do not have any settling time, right? So for a first order system, quite straightforward. 4 over a, rise time 2.2 over a, and to get the time constant, okay, 63% of the final value, right? So I guess that is the important characteristic that you need to know. Okay, and this is where I've mentioned previously, for many cases or many system itself, we still relies on testing. Okay, for a physical system, especially when you buy let's say a DC motor. Okay, and you would like to know the characteristic of it. Okay, so what one way is to, yeah, to do a testing. Okay, because the system may be closed, or you do not know what is the component inside it. There is a diode, okay, capacitors, or whatever it is, to be enclosed, and many circuit. Okay, uh, when you purchase it, they will not show you what is the exact values for that. Okay, they may blur it out with just a component value. Okay, component A1. Okay, or maybe component part 003. Okay, so it will cover up like a black box over there. Okay, therefore this testing would be important. Okay, and that testing itself, how you would know that uh, it is a first order first order transfer functions. First, when you start to do your testing, okay, you will start to use a step input. We always use a step input to do the testing because all this characteristic is based on the step input. Okay, so to identify the characteristic of a first order transfer function is that you do not see any oscillations. Okay, you just go straight up and settle. Okay, this is a characteristic of a first order transfer functions. Okay, so if you can see these characteristics, then you just use all the first order equations to describe it. Okay, so first order equation to describe it is you would use this one. Okay, so you use this, okay, to describe your transfer functions. Okay, what you need to do is to measure the time constant. Okay, the very important, the time constant and the steady state value. Okay, so you have a steady state value. Okay, after you do a testing, you check. Okay, the steady state value probably is this one is 0.72. Okay, probably. Okay, yeah, roughly 0.72, and then 63% of it is roughly 0.45. Okay, plot it down, so you roughly get mm, the A equals to 7.4, 7.7, because this what roughly 0.13. Okay, so this is how you get the A, okay, from this characteristic curve. Okay, so once you get this, then the rest is quite straightforward. Okay, so you can get the k value of your equations. Okay, the k value for your equations, because we use this step response general equations. Okay, assuming it is a first order transfer functions, right? So once we get the A, just substitute into it to find the K. Okay, so we know that K over A is equals to 0.72, which is our final value. So therefore the K is 5.54. And the overall transfer functions for this unknown system initially is 5.54 divided by S plus 7.7. Okay, so this is how we can do a kind of lab testing, okay, to identify the transfer function for the particular system. Right, so any questions before we call these sessions to an end?
No, doctor.
No,
No,
doctor.
doctor.
No,
Okay,
doctor.
so in that case, then we will stop over here and we will resume with the second order system next week. All right, so see you again next week. Is it public holiday on Thursday, Deepawali, right?
Yes, doctor.
Yes, doctor.
Okay, then see you on next Friday lah. Okay, in that case.
Okay.
Okay,
All
doctor.
right,
Thank you.
Okay,
Okay,
doctor.
doctor.
all
Thank
right,
you,
Okay, thank
doctor.
you,
right.
doctor.
See you again. Bye bye.
Bye bye.
Thank you,
Alright,
Thank
thank you,
doctor.
you.
doctor.
Stay safe.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.